Geomorphology, or the making of Earth's landscape, is really a battle between the forces that create relief or uplift and those that denigrate or destroy the Earth's landscape. One of the key processes that makes relief is the topic of plate tectonics. My focus rests on understanding the processes of how Earth works, not just the memorization of the static features. I also hope you enjoyed this geotune that one of the introductory physical geography students made at ASU. The outline for this presentation on tectonic processes is broken down into 4 topics: Alfred Wegener and the story of how a scientific paradigm changes, the structure of Earth, the different types of interactions between the tectonic plates, pulling apart, coming together, and moving side by side, and then hotspots. Alfred Wegener was an atmospheric scientist. He had a passion for understanding, documenting a concept of continental drifts, and this quote illustrates his frustration in dealing with the surrounding scientific community that fought him tooth and nail over his ideas that the continents moved. Wegener's passion led him to compile evidence gathered by other scientists, as well as conduct field work on his own. He went to Greenland, mapped the different types of rocks to see how they were similar to those found in Northern Europe. Wegener compiled an extensive array of evidence. Here are some examples: that the shape of the continents once fit together, that rock types matched, that fossils found in geologic strata matched across continents. This lifetime of work led to a massive amount of evidence favoring the notion that continents move around. He published this compilation of evidence several times, the first edition in 1915. Certainly prior to Wegener, others had wondered about the similar shape, at least the fitting of South America into Africa, especially if you take out the Niger River Delta. Sir Francis Bacon. Certainly others before Wegener had thought about the concept of continents moving. Sir Francis Bacon reconstructed the coastlines of South America and Africa, and aside from the Niger River Delta, well, you can see for yourself in this animation how nicely they fit together. From 1915 until the 1960s, the notion of continental drift had utter rejection by the geological community. Here are some of the different quotes. Wegener's hypothesis in general is of the footloose type, in that it takes considerable liberty with our globe and is less bound by restrictions or tied down by awkward, ugly facts than most of its rival theories. Utter damn rot is a famous one from the president of the American Philosophical Society, which at the time was extremely prestigious. In a nutshell, for a half-century, the paradigm of the geologists was that continents could not move and that Wegener's ideas were bogus. Today, we completely accept the notion that there are tectonic plates, essentially pieces of the crust that move around. Today we accept that most earthquakes and volcanoes occur along the boundaries of tectonic plates. There are a couple animations here that show this. One of it is earthquakes where they just accumulate over time, and the other one are volcanoes where they accumulate over time. If you click on the animations and watch them, you'll see that most of the volcanic and the earthquake activity exists along these boundaries. Today, we accept that these plates move around on the order of centimeters per year. Today, we accept that there was once a supercontinent called Pangaea and that it broke apart, including the splitting of the Atlantic. You may have heard in the news, there was a debate in the news in March of 2017 associated with the Nature publication arguing that a piece of the Earth's crust around New Zealand is a continent, at least from the perspective of plate tectonics. So I thought you would be amused by pausing this presentation and reading this correspondence, making a case that Zealandia, or New Zealand area of the Earth's continental shelf and miniature plate, is not a continent.
to me, it's an issue of semantics. There's no question that the area around New Zealand has been studied extensively and that it's a part of the whole plate tectonics picture. But whether or not you want to call it a continent or not, you can decide for yourself.
So we've jumped from Alfred Wegener proposing continental drift to the current day where everybody accepts it. It's taught in beautiful free online video series. The natural question is, why the opposition to Wegener and why the shift? It's a great example of how science works. Science disciplines often get locked into a particular way of thinking. The word that explains the mental mindset of scientists is called a paradigm. And the paradigm of geologists at the time of Wegener was that it would be ridiculous to think that continents can move around. It's also an example of how a discipline protects its turf. Wegener was a meteorologist. How could an atmospheric scientist say that the field of geology was all wrong? It's yet another great example of you gotta let the opponents die, which is what happened, and then a whole bunch of new geologists come in the 1960s with an attitude to challenge the establishment. So it's a reminder of what we'll discuss throughout this class, that the ideas that are presented in science depend upon the mental framework of the scientist. Many scientists reject this concept. They believe that data are data and you can't argue with it, but I'm of the view that data are interpretable, and what's important is not just the nature of the evidence but the way in which you think about it. And plate tectonics is a superb example of the way in which you mentally think about a scientific question constrains how you interpret it and the conclusions you reach. The geologists of the time would argue that the reason why they rejected Wegener was he couldn't answer a fundamental question of how the continents could move. It took a half century for geology to advance to the point to begin to understand Earth's internal structure, and that internal structure then allows the continents to move. Today is a fantastic period in the science of geology to understand what's going on inside by all sorts of analytical techniques. For our purposes here, what's important is that there's a crust that's about 5 miles in the ocean, 25 miles thick, and underneath a mountain chain, and that this crust is brittle. It breaks apart. Underneath this crust, or the rigid lithosphere, is a layer of plastic semi-molten material called the asthenosphere that's the upper part of the mantle. So what happens here is that the asthenosphere moves around and carries the rigid lithospheric crust like a raft bobbing on an ocean. This diagram illustrates the brittle thin crust under the oceans and the slightly thicker brittle crust under the continents moving around, being carried by the moving asthenosphere. It's one thing to see a cartoon. It's another thing to see the visualization of real geophysical data. And this is a recently published version of geophysical data analyzing subduction processes where the lithosphere is being carried on the asthenosphere as visualized by data off the coast of Japan.
It's long been thought that the radioactive decay of uranium, potassium, thorium, and other radioactive elements powers Earth's plate tectonics. But there's fairly new research that what goes on in the liquid iron is the dissolution of magnesium that then gets precipitated. And when magnesium-containing minerals precipitate, it would produce buoyant particles that rise through the liquid part, the liquid iron in the core, and accumulate. And so that this sort of denser, lighter material would create a convection pattern that would stir the core and generate Earth's magnetic field. So there's the thought that part of powering the Earth's whole plate tectonic dynamic system, at least from the Earth's magnetic field perspective, it involves the precipitation and cycling of magnesium minerals.
This slide illustrates two different types of crust. The ocean crust is denser. It sometimes goes by the name of SEMA, as shown in this crossword puzzle. A lighter continental crust, much thicker, goes by the name of CL. An issue to look at in this diagram is the thickness of the crust in relationship to how much it sticks out. You'll notice if you look under the continent that 5/6 of the continental crust is submerged, that only 1/5 of it sticks out. This is due to what's called an isostatic balance. The continental crust likes to stay in an equilibrium, and its equilibrium condition is approximately 1/6 out. The concept of isostatic equilibrium, well, you can talk about it in different examples. The floating block example. You put wood in water, and if you can stack blocks on top of one another, the thicker block will both float further down and stick out more, and the thinner block will float, and there's a condition of equilibrium where there has to be a balance from density. If you look at the diagram right underneath it, the same thing is true for continental crust. If you have a thick mountain root, more of the mountain will stick out. If you have a thinner continental crust, less of it will stick out. And this condition is in an ongoing balance. For example, if you accumulate a mile thick glacier, that mass is big enough to push down the continental crust, and then when the glacier is melted away, the crust will rebound. So there's a balance that has to continually adjust.
I am not sure if you've ever seen the Pixar short for the birds, but I think it does a fantastic job of illustrating isostasy, both the loading part when the big bird settles on the line, and then the rebound when the weighting no longer exists and the big bird leaves. So I just recommend you go to YouTube, search for the birds Pixar, and then watch the animation and think about it from the perspective of plate tectonics.
The ongoing isostatic adjustment of Earth's crust can even be seen historically. When Lake Mead filled behind Hoover Dam, the mass of the water has actually been pushing the ground down. One of the most amazing topographic features on planet Earth is the Tibetan Plateau. It's 2 miles high, relatively flat, tucked in behind the Himalaya Mountains. It's going up because the plates are too thick underneath. There's an Indian plate and a Eurasian plate, and they've been forced together so that it's double thick. To compensate for the double thickness, the Tibetan Plateau is rising. As the Indian plate has been shoved underneath Asia, the Tibetan Plateau has actually been growing to the north because the isostatic balance has been thrown out of kilter, first in the south when you have the double thick crust, and then as the double thick crust has been moving north, the plateau has been adjusting. The Appalachian Mountains were once like the Himalaya Mountains, giant, from the collision of two continental crusts. Then the young mountain range started to erode, as shown in B on this diagram. The initial erosion of the Appalachian Mountains led to the root pushing the mountain chain up, so it stayed reasonably high. But as the root became a typical continental crust, the old Appalachian Mountains wore down to the current state that you see them today. It's pretty strange to think of the Earth oozing and flowing. Maybe not so strange with the idea of the asthenosphere flowing, but the brittle crust on top actually can ooze, and we have a local example in southern Arizona that South Mountain and the White Tank Mountains and several other mountain chains in southern Arizona exemplify the concept of isostasy and the slow movement of the continental crust. In brief, Arizona's crust used to be thicker. It thinned out when Arizona pulled apart, and South Mountain has bubbled up to adjust for the thinner crust. In turn, Tempe Butte, Camelback Mountain, and other features in central metropolitan Phoenix slid off of this bubbling up South Mountain. We'll discuss this later on when we get into the details of faulting and folding. The reason for all this movement is the excess heat from the radioactive decay of elements inside of Earth. That excess heat creates the liquid core that generates the magnetic field, and there's also convection in the mantle to try and move this excess heat from the core outward. The exact way in which the mantle flows and moves in convection currents is under fierce debate. This is a view suggested by ASU professor Ed Garnero and his students in the way in which you can have circles or convection currents in the mantle, and then sometimes the subducting slabs may descend very quickly and go almost all the way down to the outer core. Please click on this link to visualize what happens when a subducting plate makes it all the way to the core as a downgoing slab. Ongoing research has shown that the splitting apart of the Earth and the movement on the asthenosphere can be initiated by vicious mantle plumes. Vertical motion can split apart the plates, as illustrated by a model in the lower left and then a real-world example with the afar in the upper right. What's interesting to me is that in the 1960s, the Soviets had this concept that vertical motion can generate horizontal movement, and the Soviet school of vertical motion was in contradiction with the United States view of lateral movement and plate tectonics, so the Soviet school was ignored. And now this new research about plumes initiating horizontal movement has completely forgotten about this ancient Soviet research. No matter how the mantle moves, we do know it does. It answers the question that Wegener could not over the mechanism of the moving of continental plates. The third topic and the major focus of this presentation is the different ways that tectonic plates interact to produce the topography that we see today. There are three fundamental types of interaction. There is where plates separate or diverge. There's where the plates converge. And then they can also move side by side, and that motion is called transform. The first type of interaction to discuss is plate divergence, or spreading apart. The most significant feature that can be seen on planet Earth are the mid-ocean ridges that spread, and it looks like they suture the Earth's oceans together. These are locations where the asthenosphere wells up and comes out in a mid-ocean ridge. The poster boy of the mid-ocean ridge is the Mid-Atlantic Ridge, a giant ridge that runs all the way from Antarctica up through Iceland. Other prominent spreading centers or topographic ridges are the Mid-Indian Ridge and the East Pacific Rise. A typical question is, look, I don't get it. Why is there a ridge? Because if the Earth was splitting apart, there should be a rift or a valley structure. And the answer is that both are true. The ridge exists because there's so much heat welling up that it just forces the entire ocean's crust to bubble up and rise. But if you zoom in right where the rift zone is, your intuition is correct that it is pulling apart, and so you get a valley or a rift zone in the center of the mid-ocean ridge, but the structure as a whole is really buoyant because there's warmth underneath, and so it all bubbles up into a very long ridge structure. The answer is it depends upon the scale that you look at. The idea of seafloors spreading apart played a vital role in rejecting the geologist's paradigm of continental immobility. In fact, plate tectonics was the renaming of this whole scenario. Rather than accept Wegener's continental drift, of course, you have to rename it because you have to own it. And so plate tectonics was the combination of continental drift and seafloor spreading. And two key pieces of evidence led the young geologists at the time to accept the new theory of plate tectonics: potassium argon dating and paleomagnetism. Potassium argon dating is a radioactive method, kind of like radiocarbon dating, but it works with lava rocks. You start with radioactive isotopes of potassium trapped within the molten rock as it solidifies. Then over a very long time period it decays. So after one half-life, 50% is decayed. After two half-lives, 75% is decayed. This technique allows the dating of ocean crusts on the order of millions to tens of millions to actually hundreds of millions of years. This is a fun map showing the ages of ocean crusts with the potassium argon dating technique. What sticks out right away is that the mid-ocean ridges are the youngest, and as you move away from the mid-ocean ridges, the rocks get progressively older. Another thing that you'll notice is none of the ocean rocks are older than around 200 million years. I encourage you to look at this animation showing how the ocean crust has spread and how the oldest crusts are towards the margins and the youngest crusts are at the seafloor spreading centers. It's important to realize that new detail gets added to the story all the time. This is a February 2009 publication in the magazine Science, where a simplified version of how the seafloor spreading occurs on the left is being modified and made more complex by new research on the right. The general story remains the same, but as you move on in life, beyond this introductory course, realize that some of the simplicities taught in this course, well, there will be complexities added in 10, 20 years from now when maybe your kids or grandkids are taking this version of the course. And I thought you'd like this fairly new video showing actual footage of eruptions on the seafloor associated with seafloor spreading. Just click on the link. But it just wasn't potassium argon dating. There's an idea of recording the magnetic state of magnetic minerals in rock called paleomagnetism. As a magma solidifies, the magnetic minerals in the rock align to the magnetic field at the time. So if the magnetic field was close to where it is today, close to the North Pole, the alignment would occur towards the North Pole. But in the past, there have been major shifts in the magnetic field, and the lava that came out in the seafloor spreading, well, the minerals in those lava align to those ancient magnetic fields. Just click on the link to see a visualization of how magnetic reversals can create mirror images of paleomagnetic signals on the seafloor on either side of a spreading center. Here are some other graphics that just illustrate the flip-flopping of the lava rocks going from the normal polarity toward the north to a reverse polarity position where the magnetic fields align to the south. The net conclusion that was obvious to the young geologist at the time was that the paleomagnetic record recorded in the lava rocks provided overwhelming evidence that the seafloors were spreading apart and that new ocean crust was being made. The last time that we had a major flip-flop was on the order of 800,000 years ago. So we've been in this state of an orientation towards the North Pole, and our condition has lasted longer than most. If you look over the last 5 million years or so in this diagram, you can see that most flip-flops occur more frequently. So we've been in a condition, and there's a substantial number of people who think we're ready to shift, and that the current movement of the magnetic pole moving fast towards Siberia at 25 miles a year may be an indication that the Earth's magnetic field is getting ready to switch again. There was a ridiculous Hollywood movie called The Core that focused on the Earth's magnetic field getting ready to switch. In reality, if you look at these diagrams published in Science magazine of the last major shift in the Earth's magnetic field, where people actually looked at a whole range of lava rocks right in this period when it was shifting from the South Pole to the North Pole, the evidence is that it's going to take thousands of years, so please don't lose any sleep over this happening. A different question altogether is, why is the geomagnetic field of the Earth generated? There's general agreement that the magnetic field occurs and is being generated in the Earth's liquid outer core, but there's not a lot of agreement in terms of exactly how this works. The diagram on the left shows a conventional concept where the molten iron core is circulating in a spiral fashion, but there's new research illustrated here suggesting that the flow pattern of the core may not be spiral but may be thin sheets. No, you're not asked about this on the quiz, but it's always important to get at the question why and the processes behind the forms we observe. Seafloor spreading just doesn't take place along the seafloors. This process of divergence opened up the Atlantic Ocean, and some people feel it's starting to split Africa, although most people think that Africa won't completely split apart, but certainly it's opened up the Red Sea. The East African Rift is a fascinating situation. So there's an animation link for the rifting and then a video story showing the footage about the East African Rift and the process of plate divergence. It's an interesting story because nobody knows if the African continent will actually split apart to create a new ocean. With all this creation of new ocean crust, the obvious question is, okay, why isn't the Earth blowing up like a balloon? And the answer to it is that the old ocean plates undergo subduction. That's the process of the remelting, the moving of the old ocean plates down back into the mantle. Subduction.
So I think the plate tectonic lecture is quite long. This is the halfway point. I suggest you just pause the presentation or terminate it and then take the first quiz on the plate tectonics lecture. What happens after this point in the presentation is the subject matter for the second quiz.
You can think about the convergent boundaries really in three different combinations, because you have ocean crust and continental crust, and there's only three ways to make them converge together. You can shove an ocean and a continental plate together, with the example being the Andes Mountains. You can combine an ocean crust and an ocean crust where the colder one goes down and you get island arcs, or you can push a continent and a continent together like today's Himalaya Mountains. Let's first look at the interaction between oceanic and continental plates. When you have an ocean crust that's denser, it goes down in a subduction zone. It forms a trench as the subducting plate moves down. There are earthquakes all along the boundary between the ocean and the continental crust. There's enough friction to generate magma melt. The continental crust is squished, so you create a whole mountain chain, and atop the mountain chain are a series of volcanoes from the magma melting.
I need to be honest with you that I'm presenting a greatly oversimplified picture of what goes on in the subduction process. This is a cartoon, an illustration from a recent publication in Nature magazine. It's a research review of recent research on the different processes that happens when you have subduction occurring. That there's hydration of the material that used to be on the ocean seafloor. It's crushed and it's faulted and it's bent, and then it's dehydrated, and then it's turned into eclogite, and then it's deserpentinized. So there's a whole bunch of complex processes that happen as the plate subducts down that are not in the quiz. It's not a part of this introductory landforms class. So I can get super complicated on lots of issues, but I draw the line on this stuff saying I just want you to get the bigger picture of how the plate tectonic processes end up creating the larger issues of the continental distribution on the Earth's surface. Not for the quiz, but just a heads up that it's much more complicated than I present in this lecture.
The Andes Mountains is the classic example of an ocean colliding against a continental plate. The forcing is the East Pacific rise pushing the ocean Nazca plate into South America, and then on the other side there's the Mid-Atlantic ridge pushing South America towards the Nazca plate. The denser ocean crust goes down. So in the collision zone there's the huge mountain chain that's thrown up from all the crunching of the crust together. And atop the mountain chain there are a series of volcanoes. You also get a major trench as the ocean plate subducts down. And so this is a profile from the latest research published in Nature magazine of the speed and the movement of the ocean crust and the continental crust in the Andes Mountains. The link provides you an animation of how the Nazca plate descends and interacts with the South American plate. At the other end of the East Pacific rise, the East Pacific rise is pushing the Pacific plate north. So at the far other end, another example of this is the Aleutian Trench, where the Pacific plate subducts underneath the North American plate in Alaska, so it creates a subduction zone. It creates a series of volcanoes in the Aleutian Islands, and it creates compression in the entire region. Our local variation of plate tectonic convergence is in the Pacific Northwest, where a tiny plate called the Juan de Fuca plate is being subducted underneath Oregon and Washington. and also underneath British Columbia, with a series of compression, of earthquakes, and of volcanoes on top. Where two ocean plates converge, the colder, older ocean plate subducts underneath, and you get earthquakes, you get a trench, and you get what we see on the surface are a series of volcanoes that pop up out of the ocean, and they look to us like island arcs, where in reality it's just volcanoes sitting atop this subduction zone where the friction and the interaction of the two plates generates enough magma to have tall enough volcanoes to actually pop up out of the ocean floor and reach the surface. These are simply two other illustrations that show the features of an ocean-ocean convergence island arc and the broader picture of how the spreading at the mid-ocean ridge will push one ocean crust, and it'll get very old and dense and cold, and it'll go underneath a younger ocean crust, creating the spatial view of an island arc. The third type of convergence that can occur will be between a continental crust and a continental crust. The only example today is where India is ramming into Asia. I like this view by Bill Bowen, where India is on the right, Asia is on the left, and the collision has thrown up the Himalaya mountains. And you can also see the Tibetan plateau, where the double thick crust is forcing that isostatic adjustment, making the plateau go up. Take a good look at this diagram. You can replicate it in your classroom with a wet paper towel. Try putting a good absorbent paper towel, wet it, wring it out, and then put it on a flat surface. Then take your hand and put it on the paper towel and move your hand like you were moving India into Asia. What you'll see is a pattern of wrinkles in the paper towel that look like the topography of the range. There's the front range of Nepal and Bhutan with the big mountains, and then you get the wrinkles on the side in Pakistan and in Southeast Asia. Try it, and then look at a map, and it's something perhaps to try in your classroom. From Professor Kip Hodges at ASU comes this latest cross-sectional view of the Himalaya process, where the India plate is interacting with the Asian plate to create this massive extruding channel of rock that is the Himalaya mountains being forced up. Although the Himalayas are the current example of continental-continental collisions, the Appalachian Mountains would be an example of an ancient collision between two continental crusts. And the Ural Mountains would be yet another example of the collision of two continental crusts. You can't discuss plate tectonics without discussing the consequences, and one of the major consequences are earthquakes, and in particular there are tsunamis. Where you have subducting plates, you get a tremendous range of earthquakes, including the potential for mega earthquakes, and that's what happened in Indonesia. These diagrams show what happens. The subducting plate moves down, and there tends to be this zone where it's too brittle for it to flow. It locks up. One big major rock kind of locks up against another, and as the rocks break apart, you can get a sudden movement or a jerk that generates a massive earthquake. When the massive earthquakes occur and slips occur, the movement of the earth in the ocean creates a push-up, a sudden rebound, where the plate will jump up and will push the ocean up. These earthquakes in the subduction zones, or it can occur from a landslide or a volcanic eruption, but most frequently these subduction zone earthquakes generates a wave that'll move very fast at about 500 miles an hour.
So I provide here a link to an MP4 file that requires the logon landforms and the password rock that shows how an earthquake in a subduction zone can generate a tsunami. So if you're interested in this issue, I think you should go ahead and take the time and watch this presentation, because it provides a lot of detailed information on how the process works.
The catastrophic Indonesian tsunami of 2004, generated by subduction in a trench off of Sumatra in Indonesia, will happen again. The energy ripple from these major earthquakes are regular events. You can see different major earthquakes that have occurred in the past, and sadly enough, we just need to be prepared. On the right hand side, you can see the raising up of Sumatra, where coral reefs are now exposed permanently. On the left-hand side shows different views of Sri Lanka that was hit by the tsunami. View of Banda Aceh in Indonesia after the tsunami. Another view of Indonesia after the tsunami hit. Hawaii will be hit by a tsunami. It happened in Hilo in 1960, and you can click on the link that shows an animation of the massive Chilean earthquake that sent a tsunami that destroyed the front of Hilo in 1960. So if you vacation in Hawaii, you'll see tsunami warnings all over the place in the form of big giant yellow speakers. If they go off, run very fast away from the beach. The link provides an animation of side-by-side motion that takes place along the San Andreas Fault. This link will get you started with understanding another type of plate tectonic interaction, and that's when the plates move side by side. In this case, the United States and North America is moving away from the seafloor spreading in the Atlantic Ocean. So it's moving from east to west. The Pacific plate is moving from south to north. This produces mostly side-by-side motion along the broad San Andreas Fault zone. But there's also some compression, and that causes the San Andreas Fault to twist and bend. This is just an aerial view of one strike-slip fault throughout the broad San Andreas transform plate boundary, where one plate's moving next to another, and in this case offsetting streams. A common issue that sometimes arises is the question of, will California fall into the ocean? It's a ridiculous concept. Look, California is continental crust. It's 5/6 submerged. It's anchored incredibly tight. There's no chance it's going to be able to move away from North America. I think you'll really enjoy the animation on the left because it shows a time sequence of how the California coastline used to have convergence, and then it was turned into the transformed plate boundary that you see today. The one on the right is just an enrichment tour of the San Andreas Fault in the San Francisco Bay Area, where you can geek out along with the scientists. The San Andreas is not the only example of a transformed plate boundary. Turkey experiences major earthquakes along their Anatolia Fault. The Dead Sea, the boundary between the West Bank and Jordan, between Israel and Jordan, is also a transformed plate boundary. But unlike the San Andreas Fault, which is, if you look on the other side is moving to the right. In this case, it's what's called a left lateral transform boundary, where if you're in Jordan and you look towards Israel, Israel is moving to the left. If you're in Israel and you look towards Jordan, Jordan is moving to the left. Related to this entire story, but not an example of an interaction between tectonic plates, is the concept of a hotspot. So rather than having collision or spreading or transform motion, this is just a plume rising up out of the mantle and melting the continental crust or the ocean crust. I'll focus here on two examples, the Hawaiian hotspot and the Yellowstone hotspot, that occur in the middle of tectonic plates rather than on the boundaries. Hawaii and the Hawaiian Islands are not an island arc. There is no subduction where the line of subduction causes the volcanoes to exist. Instead, there's just a single plume rising up out of the mantle, and as the Pacific plate moves over this fixed plume, it melts the ocean crust and generates a series of islands. In this diagram, a split screen. The bottom one is a cross-sectional view where you can see the hotspot moving up, spreading underneath the Pacific plate and melting in different locations, most typically underneath the Big Island of Hawaii and in a new island being made offshore. In the oblique view, you can see the islands getting smaller as they get older, as they get away from the hotspot, moving towards the northwest. So Kauai was under the hotspot about 5 million years ago, according to potassium-argon dating. Then as the Pacific plate moved over the hotspot, Oahu grew, Molokai, and then Maui. And most recently, just in the last 500,000 years, the Big Island of Hawaii has grown, and there's a new island being built as this hotspot continues to generate melt and volcanoes. I hope that this animation, if you click on the link, helps you understand how the Pacific Plate is moving over this plume in the mantle, and it's a hot spot. As you move away from Hawaii toward the Pacific Northwest, the islands get older and older. Eventually, as the Pacific Plate cools and the plate sinks, these ancient islands move out of the wave zone action and exist as undersea bumps. Midway exists, must have been one heck of a volcano a long time ago. But there's a fascinating kink in this record of the hotspot around 43 million years ago that suggests there was a major shift in the orientation of the Pacific Plate. An alternative hypothesis to hotspots, which is nowhere near as accepted, was proposed by a Japanese scientist where the base of the crust basically cracks. I suppose you can think of it like, I'll be gentle here. Have you ever ripped the seam of your pants in the center of the pants? You notice how when the seam begins to rip, the ripping spreads out? Well, that's the basic theme of this alternative hypothesis to explain a chain of hotspot volcanoes.
Of course, there's an explanation for the alternative hypothesis to explain the observations that led to that notion. And so some people have proposed that there's a shift in the direction of the Pacific Plate that's basically split the hotspot into two pieces that diverged and may be coming together. So you get sort of volcanoes on the eastern side of the Hawaiian chain that are plumbed to a slightly different hotspot from the trend on the western side of the Hawaiian chain that could explain the observed anomalies that might lead to suggest that some people suggested that it's not a movement of a plate over a hotspot. This is not on the quiz, nor is the ripping of the pants of the Pacific crust on the quiz. It's just to give you an awareness that even in reasonably well-supported scientific theories, there's a lot of ongoing controversy and discussion where different ideas are proposed and tested.
The alternative to hotspots is rapidly dwindling as new evidence is found in favor of hotspots being produced by superplumes. This is a publication very recently produced where there's absolutely fantastic seismic evidence of plumes of hot upwelling rock that starts deep in the mantle, and it's the origin of the hotspot volcanoes like in Hawaii. So this is some of the first visualizations of seismic evidence for the existence of the hotspots in Hawaii, Iceland, and St. Helena. It starts way deep down in the mantle, and these are fantastic evidence of superplumes. Another word that's becoming popular instead of superplumes are fat plumes. There's new evidence that these plumes originate at the very bottom of the mantle, at the boundary of the outer core. And some of them are thin, and some of them are very fat. So it's just not simple. They're thin, they're fat, they spread out, but they originate very deep in the mantle. But for now, we'll go with the model of the plume explaining the hotspots and move on to Yellowstone, where a similar mantle plume is moving up underneath a thick continental crust. So instead of melting the ocean crust with regular ease, making volcano islands every few 100,000 years or so, the mantle plume melts the continental crust and you get a big pool of magma stuck underneath the crust that erupts violently every 500,000 years or so. The chain of violent eruptions moves across southern Idaho, and some people think actually moves that the hotspot jumped into eastern Washington and the Columbia Plateau, as illustrated here, although that's a speculative hypothesis. So the Yellowstone caldera chain just reflects the building of magma underneath the continental crust. There's enough magma that gets built up every 500,000 years or so until you get a massive supervolcano eruption. This is a satellite view of the eastern end of the Snake River Plain in Yellowstone, so please try and visualize the process going on. We have the hot spot over the Yellowstone Plateau. Then, as the North American crust moves over the Yellowstone hot spot, it's fractured and basalt is erupted. And the basalt lava flow is erupted in chain of volcanoes that forms the Snake River Plain. And you can see some of the more active lava flow eruptions, especially in the craters of the moon area on the left-hand side of this image. So the trail of the hotspot is an evidence topographically and volcanically.
So this is the end of the material in the second half of the plate tectonic lecture for quiz 2. So you can go ahead and take it now.